Have you ever wondered how your computer can juggle, I don't know, a dozen different apps without even breaking a sweat? It seems kind of like magic, right? Well, it's not. It's a brilliant illusion, a high-speed juggling act that's happening inside your CPU. And today, we're going to pull back the curtain and see exactly how that trick is done.
So, think about it. How can a single brain, the CPU, run your game, stream your music, and handle a dozen background tasks all at once? The secret is a set of rules called process scheduling. This is the playbook that turns a single-tasking processor into the multitasking powerhouse we all rely on.
So here's our game plan. First, we'll look at the juggling act itself. Then we'll dig into the rule book that guides it all. We'll check out two of the simplest approaches, then level up to the more advanced strategies that are used today, and we'll wrap it all up with the big takeaway.
All right, let's dive right in. Section 1, the CPU's juggling act. We're going to get to the heart of the problem that every single operating system has to solve.
Here's the big secret. It's all an illusion. Your CPU can really only do one thing at any given moment, but it switches between tasks so incredibly fast, we are talking milliseconds here, that it feels like it's doing everything at once. The director of this whole high-speed show is a key part of the operating system called the process scheduler. So if the scheduler is the traffic cop for the CPU, what are the rules of the road? Well, you need a rule book, right? A set of goals that defines what a good scheduling decision actually is. And here's the official definition for you. Process scheduling is simply the method the operating system uses to pick the next task from the waiting line, what's called the ready queue, and give it a turn on the CPU. It is literally the brain behind the entire multitasking operation. Every scheduler is trying to juggle these four main goals. First, you want to maximize CPU use. You don't want that expensive processor just sitting around doing nothing. Second and third are all about speed. You got to minimize the waiting time for a process to even start, and also minimize the turnaround time, which is the total time from start to finish. And finally, there's fairness, making sure every process gets its chance. The real challenge? These goals often totally conflict with each other. Okay, so with those goals in mind, let's look at the first real attempts to solve this puzzle. We're going to start with two of the simplest, most straightforward approaches out there. The first method is, well, it's exactly what it sounds like. First come, first served. It's just beautifully simple. If you're the first one in line, you're the first one to get served. No cutting, no special treatment. It's fairness in its most basic form. So let's see how this plays out. Process P1 arrives first, and it needs 5 milliseconds of CPU time. We call that its burst time. Now, even though P2 is shorter, it doesn't matter. It has to wait its turn. So P1 runs until it's done. Then P2 gets its 3 milliseconds, and finally, the really long P3 process gets to run. It's simple and totally predictable. But that simplicity has a major flaw. It's called the convoy effect. Just imagine you're at the grocery store with just one item, but you're stuck behind someone with 3 overflowing carts. That is exactly what happens here. Tiny, quick tasks can get trapped behind a single massive one, which leads to really long waits for everyone else in line. So, to avoid that whole convoy mess, we have our next approach, shortest job first. The logic here is pretty brilliant. Just look at all the jobs waiting in the queue and pick the quickest one to run next. It's a really powerful way to boost the overall efficiency.
And whoa, you can see the difference immediately. Here, if we assume all the processes arrive at the same time, the scheduler picks P4 first, since it only needs 3 milliseconds. Then it runs P1, then P3, and it saves the longest job, P2, for the very end. This one simple change dramatically reduces the average waiting time for everybody.
So while shortest job first is theoretically optimal for minimizing wait times, it has this one huge practical problem. How do you know with perfect certainty how long a process is going to take before you actually run it? The answer is, you can't. Not really. It basically requires you to predict the future, which is why pure SJF is almost never used. Instead, modern systems use this idea of prioritizing short tasks as one part of a much bigger hybrid strategy.
So, yeah, the simple approaches definitely have their limits. To handle all the complexity of the real world, we need to start thinking about things like fairness and priority. And this brings us to some much more advanced solutions.
So, let's talk about priority scheduling. This is just like a VIP line at a club. Some processes are simply more important than others. Think about a critical system function versus, say, a background file download. The scheduler gives these VIP processes a higher priority, which lets them skip right to the front of the line.
In this example, just remember a lower number means a higher priority. It's a little counterintuitive, I know. So P2 runs first with the highest priority of 1, then P3 gets to go with priority 2, and finally poor P1 with the lowest priority has to wait for both of the others to finish up.
That this creates a dangerous new problem, starvation. See, if high-priority tasks just keep arriving, a low-priority process might get pushed back in line over and over again and literally never get a chance to run. To prevent this, systems use a really clever trick called aging, where a process's priority slowly increases the longer it's forced to wait, which eventually guarantees it'll get a turn.
And that brings us to what is maybe the most influential scheduling algorithm of all, round robin. This is the ultimate let's just be fair approach. Instead of letting one process run all the way to completion, everybody gets a small, fixed turn on the CPU. We call that a time quantum.
All right, let's trace this cycle. Let's say we have a time slice, or quantum, of 2 milliseconds. P1 gets the first slice. Then it's P2's turn. Then P3's. After P3 is done, the scheduler cycles right back around to P1 for its next 2 millisecond slice. This just keeps going and going until all the processes are finished. By giving everyone a small, regular turn, the whole system feels incredibly responsive. The beauty of round robin really is its fairness, and that's why it's a cornerstone of pretty much every modern operating system. But everything hangs on the size of that time quantum. If it's too long, it just starts to act like first come, first served. But if it's too short, the CPU ends up spending more time switching between tasks than actually doing work. Finding that perfect sweet spot is absolutely critical. Okay, we have definitely covered a lot of ground, so let's zoom out for a second and put all these different strategies into a single, clear picture. So here it is, the final cheat sheet. Each of these algorithms is a specific tool for a specific job, but the real takeaway is this. Modern operating systems don't just pick one. Nope. They use a sophisticated hybrid, something like having multiple queues, maybe a high-priority round-robin queue for interactive stuff like your mouse and keyboard, and a lower-priority FCFS queue for big background tasks. They mix and match these strategies to get the best of all worlds.
So the next time you're seamlessly switching between apps, you'll know it's not magic. It's an incredibly fast, sophisticated juggling act managed by a scheduler. Which makes you wonder, given the need for both responsiveness and fairness, which combination of these strategies do you think is running on your phone or your computer right this very second?